Today, we're diving deep. We are going right down to the metal to see how a computer actually thinks. We're going to follow a single line of code as it becomes this precisely timed electrical dance, all happening inside the classic 8085 microprocessor. Seriously, think about it. We type, we click, we do all these complex things, but what is physically happening down on the silicon? How does a chip turn our commands into real actions? Well, that's exactly what we're going to unravel today by looking at the fundamental rhythm that powers every single computation. You see, at the highest level, every single processor, whether it's this classic 8085 or the beast inside your smartphone, operates on a basic repeating rhythm, and that rhythm is called the instruction cycle. Think of this as the processor's entire job description, boiled down to 3 simple steps. First, it fetches an instruction from memory. Think of it like grabbing the next line in a recipe. Then it decodes that instruction to figure out what on earth it's being asked to do. And finally, it executes the command. That's it. This loop over and over, billions of times a second, is the foundation for everything. Okay, so that 3-step loop is our big picture. But now let's zoom in a little. You see, each of those steps, especially the fetch and execute parts, are actually made up of even smaller, more basic operations. And these are what we call machine cycles. So what's a machine cycle? It's one single fundamental action. It's the processor talking to another part of the system, like reaching out to memory or talking to an input or output device. If the whole instruction cycle is our recipe, then a machine cycle is just one step. Like read 1 cup of flour from the pantry. And for the 8085, its entire vocabulary consists of just 5 of these basic actions. It can fetch a command or an opcode, which is its most complex task, taking 4 little ticks of its internal clock. Or it can do one of 4 simpler things that each take 3 ticks: read from memory, write to memory, read from an input, or write to an output. Seriously, every program, no matter how complicated, is just a long sequence of these 5 basic cycles. So let's zoom in one last time, down to the most fundamental unit of all. If a machine cycle is one step in our recipe, what's a T-state? Well, a T-state is the single tick of the kitchen timer that keeps the whole operation perfectly in sync. And this isn't just some abstract idea. A T-state is a real physical thing. It's one complete pulse of the system's clock, a wave of electricity rising and falling. This is the processor's literal heartbeat. So here's the key takeaway. Every single machine cycle takes a very precise number of these T-states, these heartbeats, to finish. Fetching the main command, that takes 4 T-states. A simple memory read, that takes 3. This perfect, predictable timing, well, it's everything. Okay, so how do we actually visualize this dance of cycles and T-states? Well, we use something called a timing diagram. Now, I know it looks complicated, but it's really just the sheet music for the processor. It shows us exactly what every signal is doing at every single T-state. And this right here is the single most important cycle of them all, the opcode fetch. Why? Because every single instruction, no matter what it is, has to start with this cycle. This is the processor reading its next command. Let's just walk through it. In the very first clock tick, T1, the CPU puts the memory address it wants to read from onto a set of communication wires called the address bus. It's basically shouting to the memory, hey, I need the instruction you're holding at this exact location. And here's where we see some really clever engineering. To save pins and make the chip cheaper, the 8085 uses the same wires for both addresses and data. So how does it avoid confusion? With a special signal called ALE, or address latch enable. You can think of it as a traffic cop. It pulses high only during T1, and it's basically shouting, hey everyone, what's on the wires right now is an address. Latch it, remember it, because data is coming next. So once the memory has latched that address, the bus is free to be used for data. During the next 2 clock ticks, T2 and T3, the memory finds the instruction and puts it back onto those same wires. The CPU's read signal goes low, which is its cue to grab the opcode from the bus. And that 4th T-state, that's for the CPU to catch its breath and figure out what it just read. All right, so now we have all the building blocks, right? We've got the big instruction cycle, the smaller machine cycles, and the tiny T-states. Let's put it all together and see how this actually works by tracing a couple of real 8085 instructions from start to finish. Our first case study is a really common one. MVI, B43H. All this means in plain English is move the immediate value 43 hex into register B. And a register is just a tiny, super fast storage spot right inside the CPU itself. This is a basic load this data kind of command. Now, in the computer's memory, this instruction isn't just one thing. It takes up 2 bytes. At memory address 2000, we have the opcode 06H. That's the machine code for MVIB. Then, in the very next spot, address 2001, we have the actual data we want to move, which is 43H. So how does the 8885 execute this? Well, it always starts with an opcode fetch cycle to grab that 06H command. That takes 4 T-states. The CPU then decodes it and realizes, hey, wait, I need some data to go with this command. So it performs a second machine cycle, a memory read, to go get the 43H from the next address. That takes 3 T-states. So you add it all up, 4 plus 3, this one simple instruction takes a total of 7 clock ticks to execute. Okay, now for something a little more complex. STA526A. This instruction means store the value from the accumulator into memory location 526A. The accumulator is a special, primary register where the CPU does most of its math and data manipulation. So this command is all about writing data out to memory. And here it is, the full timing diagram. Just a few minutes ago, this might have looked like complete gibberish. But now, you should be able to actually read it. You can see it's not one giant, complicated operation. It's just a sequence of the simple machine cycles we've already learned, all strung together. Let's trace it. It starts, of course, with an opcode fetch. That's our first 4 T-states. The CPU decodes the STA command and knows it needs a full 16-bit address, which is stored in the next 2 bytes of memory. So it does 2 back-to-back memory read cycles, one to get the low part of the address, 6AH, and another to get the high part, 52H. That's 3 T-states each. And finally, with the full address assembled, it performs a memory write cycle to send the accumulator's data to that location. That's another 3 T-states, for a grand total of 13 clock ticks. See? You can read the sheet music now. So we've gone all the way from the big picture down to a single clock tick, and all the way back up to a full instruction. But why does any of this nanosecond level timing actually matter? It matters because its intricate clockwork is the shared rhythm for the entire computer. It's what allows totally separate pieces of hardware, the CPU, the memory, your keyboard, to all communicate flawlessly. It guarantees that when one chip sends out a piece of information, another chip is listening at that exact nanosecond. Without this perfect timing, you don't have a computer, you have digital chaos. And that leaves me with one final thought. The basic principles we've just walked through for this nearly 50-year-old chip are still fundamentally true today. They're happening on a scale that is almost impossible to comprehend. So it really makes you wonder, with billions of transistors and dozens of cores, what does the heartbeat of a modern CPU even look like?